Hi, everybody. Welcome to this chapter 7 of Programming Quantum Computers. We have a small group this week, but we know some people watch online. So if you're catching up online, welcome. And if you're here in person, great as well. So we are going to take this chapter that we were discussing before we started and kind of partition it into two parts because in my experience with the chapter, even though I've read it a couple of times, I really struggle with the concepts because I don't have the background in some of the references that are mentioned. So again, trying to humanize the book if you're following along with us. We're going to start with the chapter itself and really just take the first part of it and go through. So I'm going to go ahead and share my screen. Can you guys see, are you guys seeing the book?
Looks perfect.
Yeah, okay, great. So one of the techniques that I use in this book in general is I sometimes go to the end. As we were discussing, both of you guys have some context for what a QFT is in relation to other types of transforms. I did not. And so what I'm going to do is I'm just going to jump to the complete end of this chapter. And it gives a little bit of context, especially as it relates to, I can talk and go here, there we go, as it relates to the last chapter. So in the end of the chapter, it says, in this chapter, you've learned about one of the most powerful QPU primitives, the quantum Fourier transform. In the previous chapter in 6, we were doing the AA, the amplification primitive. So that was allowing us to extract information about the discrete values encoded in the phases in the register. The QFT primitive enables us to extract information about, and this is the key word, you can see it's italicized, patterns of information encoded. So I think that for me, it was helpful to really think about this as I worked through the chapter. So previously, that primitive, the AA, was we got values out. The QFT, we get patterns out. And they say here, the authors say that later in the book, chapter 12, the QFT is the core of some of the most powerful algorithms we can run, including something called Shor's algorithm, which really kind of, as they say, kicked off all interest in, or a lot of interest in quantum computing. So I'm just going to go ahead and go back. So the key word to think about here is patterns, getting patterns out of the register. So as we're going through this, it tells us that in the beginning that we can access hidden patterns and amplitude amplification. That was what it was in chapter 6. We could turn the phase differences into readable differences in magnitude, so single values. In the QFT in this chapter, it has a way of manipulating phases. So we're going to do phase manipulation. And then as we were talking about last week, this QFT primitive can help us to compute in superposition. And really, that's a big part of the power of the QPU. Because of course, when we read something, then we're done, because we're back in sort of the normal world. So being able to do manipulation while we're in superposition is part of the power of this. And it talks about, we're going to be using complex superpositions of a register. So the first example the authors give is they show this 4-qubit register that has one of 3 states. It has A, B, or C. And they point out that it's not the same A, B, or C in that we were looking at in chapter 6. And then they, remind us that we can see the states are different, but the magnitudes are the same. So by state, they mean basically the line, whether it points up or down, but all the magnitudes are the same. So that's what we're starting with. So, and then they point out with amplitude amplification isn't going to help us because the phases are all the same. So we have to somehow do some sort of computation on the lines, basically. And they do have a sense of humor. But the QFT primitive comes to the rescue. Cue dramatic music. La la. So applying the QFT, to our register, and the QFT is a function, before readout would transform the states A, B, and C into these results. So they're saying this magic function that they're going to show us how it works in this chapter allows us to get meaningful information out of this register where we have the magnitudes that are the same. And so that kind of is the starting point. All right, so it tells us we can immediately and unambiguously determine which state we started with using a single read. Q of T is a great relationship to the input states. And then it tells us in state A, the relative phase of the input state returns to 0 8 times. Now we don't really know exactly how that works yet, but that's what QFT is measuring. In state A, relative phase is the input state returns to 0 8 times. And the QFT allows us to read that value 8 out then. In B, the relative phase rotates back to its starting, so it's rotating. Somehow it's measuring the lines, the rotations. And the QFT allows us to read 4 because it's 4 times. And C is going to be another value. And so that's the first code that they want us to work with. So if I go over and I have this code here, you can see that we start with A. And so when we work with A, we're going to get 8 because we start here and then we're prepared and the magnitudes are all the same, but I forget the technical term for this, the lines, the direction of the lines, so the phase are different. And then the QFT, which again, we don't really know how this function works yet, but we know when we apply it, it's able to read out that this value here, these values are rotating to the count that is 8. So now if we set it to B, again, they're really telling us more the what rather than the how at this point, like what you get. So you start with B, and there again, all the magnitudes are the same, but you can see the lines are in different positions. So there's going to be some sort of different rotation. And then that result is 4. And so on with C. Again, same magnitudes, different lines. And that result is 2. And then I think that means D there. So can't remember if I put that in or they did. And then D, again, you can see now they're all the same. So let's see what that does. That returns 0. So now we have in the center here this if, which basically tells us what the condition is looking for. So that kind of gives us a hint of how they're measuring here. But again, they're not really at this point saying this is how this works. They're just basically saying this is what it does. So I'm going to pause here and see if either of you have anything to add to what I mentioned about this code in this 7.1.
One thing that I think is kind of interesting is how they did the encoding. So like if you go to the section that says B,
Yep.
go ahead and set it to B and run it so we can see the circuit. And so it shows that there's 2 phase operations, one that's a 90-degree phase and one that's a 180-degree phase. And based on doing these 2, why don't you step through it? So go after the had.
Yep.
And then step through the first one. And so that shows basically half of the values moved 90 degrees. And then if you do the second one, now you had half of the values move 180 degrees, but not the same ones.
Yeah.
So some of the ones that had moved 90 degrees actually moved an additional 180 degrees and are now the yellow ones. So I thought that was kind of interesting how to set these up, and then the C1 is more more of that because there's a 45-degree angle involved. So I thought that was kind of interesting as far as the setups were concerned.
Cool. Anything else to add?
No, I thought that was interesting too, and I felt like, oh, it's so simple, and I thought we had learned that already, but Nuri had asked the question when we were looking at the amplitude amplification,
Yep.
if reversing that somehow messed up the phases, or I don't remember his exact question, but I think this is what we couldn't remember how to do. How do we set up the phases in a great test environment to look at that stuff? And here, within a few pages, they made it look so elegant.
Cool. Cool.
Yeah.
Okay, good. All right. So that's the start. All right. So then they have a tip. If we want to apply the QFT primitive, we can use the built-in function, and we can apply it globally or as a method on the QInt object. So that's similar to these functions that they're creating for us. And again, you know, one of the things that we haven't been doing a huge amount of is once we've got this function, we just sort of look at it and we know what the operations do. But this was creating for us, and something that, you know, if we were using this in any sort of actual situation, like using the IBM simulator, we would then go and look like we've done in previous weeks to see what this actually decomposes to. So it basically, again, we're just getting a higher level function and seeing how it helps us with computing and being able to get the results out when we're in superposition. We're not really concerned with the details, which we would be if we were really using this, again, as something Nuri said, because of the overhead. So then they go into these Fourier transforms. So they give the context of if you're using the QFT, it's very similar to something from what's called classic signal processing called the discrete Fourier transform. And it talks about that's something that you would see if you're kind of an audiophile and you were working with a graphic equalizer and a sound system. So the DFT, as they say, allow us to inspect the different frequencies contained within a signal. And the DFT is used to inspect more conventional signals. The transform it applies is identical to the QFT's mathematical machinery. Again, they're telling us this, assuming that we have a background with this. And the two guys here do, I don't. And so it's more difficult for me. When we were talking about this, Matt was recommending that, and he said that he actually watched some YouTube videos on DFTs, and I'm probably going to do that. So anyway, so it's saying it's easier to build intuition with a more tangible DFT, so we're going to start there. And then an implementation of DFT is the FFT, which is the fast Fourier transform, and it's the fastest method. And it's used in comparison from, I think, classical computing and quantum computing. Then they go on to say the FFT shares a similarity with the QFT, and that it's restricted to the power of 2 signal lengths, which I'm not sure why that is important, but I'm sure it is because it's in the book. So we've got the definitions here. For the QFT, I'll note it's the same as the DFT. It operates on signals encoded in quantum registers, of course. Okay, so now the next part is they're talking about the magnitudes and relative phases. That would be the proper term for the black lines, the relative phases in quantum registers as signals. So then they're going to be a little bit more explicit about what it means for a quantum register to contain frequencies. So it shows the 4-qubit register state in 7.3. And when I look at this, if you notice the relative phases, it kind of almost seems like it's moving, like because the way that it is encoded. If you look at it, you can almost go do, 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 do. You can see it. You can see going how it could be representations of points of rotation, and that's what they're talking about. So that's state C. It says if we look along the registers from left to right, the relative phases of 2 to the 4th equals 16 values go through 2 full anti-clockwise rotations. We can think of the relative phases on a register representing a signal that repeats twice per register. I don't know about you guys, when that clicked into me, I was like, oh, I get it. Did you guys kind of have that same thing when you were looking at it, when you kind of could literally see it?
Yeah.
Yeah,
Yeah.
definitely.
Yeah. So that was super helpful to me. So, and then they go on to say, this is giving us an idea how a quantum register might encode the signal, having some frequency associated, but the signal is tied up in the relative phases. Okay, so we can't just read it because in quantum that destroys it, right? So we have to do something more fancy. So, and that fancy thing is the QFT. So again, this was kind of a aha moment the first time I saw it. So I was like, okay, it's going around twice. I get it. So I think if I'm understanding correctly, that is what they're trying to communicate here. So, and they're saying that. So the frequency of repetition is twice. And then they show the QFT function. And then they have this example showing that. So let's go out to the code. So again, just running this code. Okay, so we start here, and so, and then I'll just prepare. I like that you had add there, Jeremy, to see how it's being prepared. And then you can see, like literally, woo, it's going around once and twice. So once we apply this, 2. Kind of beautiful, isn't it? So is there anything that you guys did to play with this code more than what was here? To me, when I went through it, I was like, oh, I see how this works.
Yeah, that's kind of what I did too. I wasn't really changing things because I was treating QFT as, I'm not trying to understand the circuit for the QFT. I'm trying to understand more intuitively what it does, because it sounds like QFT is kind of a primitive operator that we can apply in the future, which we don't know what that feature is right now. So rather than trying to figure out, okay, what is this circuit doing? Just kind of looking at it and saying, okay, like you said, oh, I see it's going through 2 rotations. And when I run it through the QFT, that's the result that I get. So we can actually turn the relative phases into something useful. Now that implies that our relative phases are in fact in kind of this fairly simple pattern in this case. I know the book talks more about combined frequencies a little bit later.
Yeah. It starts out simple, but then you're right. I mean, obviously, it doesn't have to just look like so symmetrical. Basically, there can be different varieties, but it's starting out in a very symmetrical way so that you can get the visual intuition of what the QFT is doing. Now, one thing I did just to play around, and it didn't really make much sense, but I was playing around with the number of qubits just to see if that helped me understand at all. And it wasn't really super necessary for this, but it was just something that I did to play around with this. So at this point, it didn't help me because it got into a more complex state than I wanted to see. But sometimes curiosity kills the cat. Matt, is there anything else you want to add here?
No, I'm laughing at your curiosity kills the cat. I heard a quote yesterday I'd never heard before. And someone said, why are you looking for order in this? Great minds have gone mad looking for order in all the wrong places. I thought, you know what? That hits a little too close to home. So no, I agree. And I noticed that the QFT circuit was vastly changed when you went down to 2 qubits. And I almost wonder if there's a minimum number of qubits you need for the QFT to stop, before it starts working.
Yeah.
Or if it just works in general.
Yeah. I mean, I was just playing around with it, and I did notice that too, because again, I always want to see like what's generating the QFT here. It's obviously some sort of loop. So I was just playing around, but then I thought, well, this isn't really helping my understanding of the problem. So I'll just go with 4 for right now and figure it out later. So, okay, cool. All right. So, we did that one. And operations often need to use distinct input and output for reversibility. QFT occurs on the same register that provides its input, so it's a transform. and it can operate in place because it's inherently reversible, which is the second part of this. The one thing that I was thinking is some operations seem to require scratch qubits, and this does not. And I know from reading ahead and from just other reading that that does affect the practical usability of the different operations. And the fact that this doesn't seems to me that it's more important. And the authors keep saying how important this is. So there's an efficiency when you can go directly on the register, which again, I do not understand the why. I'm just trying to understand the what and the how. Okay, so you might be wondering why we care about a tool that helps us find frequencies. How can this help us solve practical problems? See, it's telling us it's versatile. So is that all there is? Go into a register and get back its frequency, sort of yes and no. And so far, we've been looking at a well-defined frequency because they did that on purpose. So now we're going into less regular patterns. So we look at this pattern that is not as symmetrical. And then they point out that the values that are pointing down is equal to amplitude having a negative value. So we have positive and negative values. And then they tell us here that the square wave equivalents of the example, they are the square wave equivalents of the example that we first started with. And they're oscillating the same frequency, the relative phases flip-flop between positive and negative rather than varying continuously, so positive, negative. And they tell us that the result is going to look like this. So it's flip-flopping positive and negative through an oscillation. And the result is not as clear. All right, and so they're calling this square wave input. And they're saying that we can produce this with the HAD with the 180. And this gives us the square wave state. And then we apply the QFT. So we have this variable wave period that we can select which state we want to produce. So from 7.6. So the wave period. All right, so this is 7.3. All right, so we look at this and we had it, and then we do this 180. So this gives us the flip-flop. And then we have this variable wave period, and it's by default set to 1, which in their code they say is A. And so then we see 8, because that goes back to the original one where it was 8 rotations, if I am understanding correctly. And then if we set the wave period to 2, it is not as clear. So I am kind of at this point of, okay, is the point of this to be that there are some results that are not as readable? Is that what they're going for here? How do you guys take this?
So kind of the intuition that I get from this is from history working with analog synthesizers, which was many, many, many years ago. And so, I understand the idea of the difference between a sine wave and a square wave. So a sine wave is kind of a nice curve, which is sort of what we saw in the first circles where, they're kind of going around in increments.
Okay.
And eventually getting there. In this case, if you go back, right after the prep section.
Here. Yep.
So a square wave just goes from high to low with no nice curve. So it's like beep, 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 beep. Yeah, that's my technical jargon. So in this case, it's like staying high for 4.
Yep.
And then going low opposite for 4, and then coming back up for 4, and then going down for 4. So it's a very, kind of square wave.
I see. Thank you. I see what I see now. I
Yeah.
understand. Yeah.
And there's kind of a diagram a little bit later that
Mhm.
kind of doesn't show it real well.
Yep. I understand. I
Yeah.
understand.
And then the result is inconsistent because, well, later on they'll tell, like, when you're doing Fourier transforms on this type of data, you basically get a mirror effect.
Hmm.
So it's basically saying, well, kind of the correct answer here is 1 because that's the most, the most one that's there. The first one, when we just have the back and forth,
Hmm.
there's no mirror in this case because we end up, it makes the circuit 8 times. And so that's kind of all there is. But change the wave period to 2
Yep.
and then go after the preps step.
Hmm.
And so here we can see kind of intuitively that it's going back and forth. It goes back to 0 4 times.
Hmm.
And so we have a 4 that comes up, but we also get the mirror, which is basically kind of the 16 minus 4.
Hmm.
And so that's why we have a thing at 12. And so theoretically, if we kind of know what we're looking at, we can ignore the 12 value as a reflection.
That is so helpful. Thank you. That I now see what the wave period does. I did not make that connection. Matt, do you have anything to add?
Yeah, if you go back,
Yep.
I'm trying to see where to go back to. I guess after the prep period.
Yep. What value do you want for the wave period?
Oh, 2's fine.
Okay. So go here. Yep.
And yeah, one thing that got me, so yeah, you can sort of see that square wave
Yeah.
in there. And I wish they had made this like a diagram. Can you see this?
Yeah.
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 You can actually, yeah. So the amplitude literally is,
Yes. You could see it. There was a light bulb in my head when Jeremy was talking. I was like, oh, I started seeing that. That's
yeah.
awesome.
Whereas in the other example where they're going, around, all the way around,
Yeah.
it's backwards. So this is gonna be a bad drawing, but it was more discreetly doing something like this. You had a really nice sine wave and said, oh, I can see this wave repeats every 2, 4, 8 cycles. And they admit in the book, okay, these are really, simplistic. These are coming out with clean answers. And then they jump right to the square wave. And I know in math, when you're trying to graph things and you're learning about graphing and coordinates, math has a real hard time with things like this. Because it's like, well, right before that, it's 1. Right after that, it's a -1. What is it right in the middle? I don't know. It's unknown. It's imaginary. It's infinite. Who knows? And as a math student, you're like, I need to know what that is. And so I think we're seeing some noise with this. And let me clear all this out. But there we go.
And thanks for that diagram, Matt. That was awesome.
Oh, thanks. And he goes later on in the book, and one thing that got me is, I guess the D and DFT is discrete, and you see that they take little samples along the waveform that they show later on. And it's like, oh, okay, this is where things start to either make more sense. The more we sample it, the more information we have to come up with nice and neat models that represent what our frequencies are. You go back to when everything got digitized and they're taking records and track tapes and putting them on compact discs, and you had the purists and oh, that doesn't sound like real music. Well, no, you're digitizing something. And if you digitize it with a really low or poor sample size, it's not going to sound great. And so the more, so this is where I kind of see them going. If we have more and more qubits to work with, we can do some really pretty high-end stuff. But yeah, I kind of went off field.
No, that's cool. No, that's cool. It's interesting. Again, you guys have the math and the electronics background that I don't, and so this is super helpful. This is why we have a book club, so we can do this together. So okay, so now we're going to go into these drawings of these waves. So for reference, talks about the DFT. As Jeremy was saying, it acts on discrete samples taken from a signal, whether it's musical or digital image. And DFT will work on complex signals as well. Because as you were saying, that to have that measurement, you're going to have complex numbers. And they start to talk about, even though they're not showing them to us, they say that is what is happening under the hood here. And they say specifically, when you see complex number, you can think of a single circle from our notation with the magnitude and phase. They're trying to abstract this to a higher level so it can be more accessible, but they really are skipping over a lot of the math. So now they're showing the simple sine wave, and the samples are real numbers, and there's a well-defined frequency, pure tone. And then they say we've taken 256 samples of the signal. So those are the dots. Each sample is stored as a complex floating point number with magnitude and phase. The imaginary part will be 0, and they show you the example. Each sample is stored as 16-byte complex float, 8 bytes for real, 8 for the imaginary part. The signal will fit in the 4096 size buffer. We need to keep track of the imaginary part. The output of the DFT will be 256 values, so the dots basically. So, and this is what Jeremy was talking about, the actual, and then Matt was drawing the actual wave itself. So the magnitudes of the complex output tells us how significantly the frequency contributes, and that was the nice audio boop, boop, that Jeremy added. The phase tells us how much these different frequencies are offset, and shows us what the magnitudes look like. And then it shows the measurement in hertz there. And then it gives a warning. We're looking at the 2 peaks. You'll notice they're surrounded by small non-zero values. And the DFT is limited to a finite number of bits. We can see peaks of non-zero width, even where the signal contains only a signal frequency. It's worth being aware the same can be true for QFT. So, and that I think is what you were talking about, Matt, with the number of qubits that you could have loss, if I'm understanding correctly. Yeah?
Yeah.
Yeah, okay. So the DFT is transferring the signal into frequency. We can see the frequency components. The input signal completes 8 full oscillations. Over the sample time, we expect to have a frequency of 8 hertz. That's cool. I can't get that now. That's neat. This is precisely, I'm sorry, I'm just like learning. I'm a little slow sometimes. The DFT returns to the output register. Okay, so looking at our example, you notice the 248 hertz is the elephant in the room. Alongside the expected 8 hertz, the DFC produces a conspicuous second, and that's what Jeremy was talking about, mirror image in frequency space. This is a property of the DFT of any real signal, where the samples are real numbers. In such cases, the first half of the DFT is useful. Take note of the first 256 divided by 2, 128 points that it returns. Everything else, it will be the mirror image. And that's exactly what you said, Jeremy. So good. And then it shows the examples here. And now it talks about, had we used a complex input signal, that's where we're going in this chapter, because there wasn't enough already. we wouldn't see this symmetry effect, and each of the 256 data points would contain distinct information. That's actually a super important point, because they're leading us along with symmetry so that we can get the concept, but the real world, we're usually going to have complex. It's going to be a lot more messy. All right, then the caveat, interpreting the output of real versus complex holds true for QFT. Let's look back at the example. You'll notice examples in 1774, there was no such symmetry. We only observed a single peak in the output registers corresponding. It's because the signal being encoded in the relative phase of our input register state was complex, so no symmetrical redundancy was seen. Yet we could prepare real signals in our register. Suppose the signal we planned in QFT was encoded in magnitudes for output QFT or input QFT instead of the relative phases. So suppose the signal we planned was encoded in the magnitude. So now the circle sizes are different. Instead of the relative phases. And the relative phases are either up or down or nothing. The input signal is entirely real. Don't be fooled by the fact that the relative phases change across the state. Recall that the phase of 180 is a negative. So all we have here are positive and negative numbers. Okay. Well, my natural question, and I think it comes later in the chapter, is what if it's just not positive and negative? Can we also have phases that are somewhere in between? I would think we can. So,
And that's, yeah, I think that's where he's getting to, because again, my math was so long ago. When they start talking about imaginary numbers, I forget what most of that means. But right there, what you just read signaled it to me. I'm like, oh, okay. So if the phase is either purely positive or purely negative, then we don't have any imaginary information.
mhm.
But if the phase is anything other than 0 or a 180, that's where that imaginary comes in. And those first few examples, we had all those different
Yep.
degrees in between, right?
Yep.
And we didn't get that mirror image. So I guess that's what he's saying, is that imaginary part, which again, to me is confusing, is in that when that phase is something other than 0 or 180.
Yep, that makes sense. All right.
I don't know that he's showing anything here other than an example of a completely real non-imaginary value.
Again, I think what the authors are trying to do is chunk this into subsets so that we can pull it all together in the end when it's all, when everything can be varied, when it's extremely complex. Because I think, and it's logical to me that we have to go through each part of it. So yeah. Okay, so the next part is applying the QFT to the real input state. We find the output register exhibits precisely the mirror image effect that we saw with the conventional DFT. So we'd only take the first one in this case, if I'm understanding correctly, because the second one would just be a mirrored image and it wouldn't be important for our computation. All right, so we need to take care of how we interpret it, where input register encoding is in phases or magnitudes. Okay, that seems to me to be pretty important. So in a QFT, we need to understand if our input register encoding is in phases or magnitudes. And my question is, could it be in both? I would think it could, but maybe it can't. All right, so we've talked about DFT and QFT showing us what frequency the signal contain. The transforms are actually telling us the frequencies, proportions, offsets of simple sinusoidal components that we could combine. Most of the example input signals that we've considered have actually been simple, yes, with simple frequencies, yes. As a consequence, our DFT and QFTs have yielded single well-defined peaks, yes. You can build that from one sine function having a frequency. One of the most useful things about the DFT is we can apply it to more complex signals that aren't obviously sinusoidal. So as the magnitude of conventional DFT performed on input signal containing sinusoidal boy, that's a fancy word, sinusoidal oscillations. Wow, say that 3 times fast at 3 different frequencies. It's easier to look at the picture than to say the word. But that does make sense to me now because of you guys' wonderful explanation of why this becomes this. Makes sense. Okay, it's worth taking note of the value of the DFT, QFT corresponding to 0. This is known as the bias. Reveals the baseline value that the signal oscillates above and below. They've all oscillated about 0. They've had no DC bias component. Okay. Not only does the DFT show us that these 3 frequencies make up our signal, but the relative heights and peaks tell us how significantly each frequency contributes to the signal. By inspecting the phase, we can learn how the sinusoids should offset from each other. And it's a real signal, meaning no imaginary numbers. We can ignore the second half. Okay, making sense. One particularly common useful class that we can look at are square waves. And that's what we were talking about a little bit earlier. And that is shown like this. And now we're going to look at an 8-qubit register, or qubit, giving us 256 state values to play with. And we prepare a square wave with changing the phase here at this location. And let's look at that. All right. And so when we look at this, that is our example. So we have a bigger, we can't see the whole register down here, or can we? It's cut off, I think.
Yeah, it's cut off. I've tried to make it bigger
Yeah.
and you only get so many circles.
Yeah.
Yeah.
Oh, wait, you're getting more.
Well,
That's
it's-
not the only thing you can do.
Yeah.
But I think there's a
but
bug.
I mean, I'm gonna have to go like this.
Yeah.
Yeah, it's not really helping me here. Okay, so fine. Maybe I'll look at what the book is showing. So it's supposed to look like this, okay, which is what it is. So all the magnitudes are the same, and it's pure. It's either up or down. Okay, and then oh yeah, I remember this one. This. Okay, let's go back over here. Then once we do the transform, but it's really hard to see.
Yeah, the book does a better job. of
Yeah, basically you want to look at the book. So basically this is that.
Yes, on its side.
Yeah, yep, yep. I can see that.
And
I
the
can see
square
it.
wave is also. So that picture on the left
Yep,
is what the inputs, I guess, look like after the prep phase.
yeah, so it's either up or down, or
Yeah.
down, right? Yeah.
Mhm.
So, well, I mean, that's a leap forward that I get that this is basically, I can go, sorry, go back to where we were there. That this is basically that,
Mhm.
and
Mhm.
then the result is that. Okay, that makes sense. Awesome. Okay, so now, all right. Recalling that the green circles represent negative, you should, that's funny, you should hopefully be able to convince yourself that the signal is both entirely real and completely analogous to DFT.
Mhm.
So, okay, I'm a hopeful person. I have convinced myself. Okay, so the registers, this next part was really interesting to me. This registers precisely the square wave DFT from 715 with each component and frequency space being encoded in magnitudes and relative phases of the states of our QPU register. This means that the probability of reading out a given configuration of the post-QFT register is now determined by how strongly a given frequency contributes to our signal. And then they're plotting, you can see the similarity to the conventional, which we saw there. And then this is the sort of killer thing here. Like, why are we doing this, right? So basically they showed us that the QFT is implementing a DFT on a QPU. And then they're saying, okay, it's finicky, so why are we doing this? And then they say it's important to remember that our motivation is primarily to manipulate phase encoded computation rather than to provide FFT. So here's where the pedal hits the metal. The computational complexity of QFT compares to the FFT, since the QFT turns out to be far, far faster. Okay, they don't say this, but my assumption is that you could implement an FFT with classical computing, right? That's
Yes.
what I would think, right? And so the QFT is fast. We're talking about the speed. The runtime of the algorithm increases as we increase the size of our signal in terms of the number of bits. For practical purposes, we can think of the number as fundamental operations the algorithm uses being equivalent time takes to run, since each operation takes a fixed time to act on the qubit. The FFT requires a number of operations that grow with the number of input bits. And the formula there, leveraging the 2 to the m states available in the register, it uses a number of gates that grows as the formula there. So pragmatically, finally, the reason I'm here, this means that for small signals, less than 22 bits or 4 million samples, the conventional FFT will be faster even using a laptop. But as the size of the input grows, the exponential advantage of the QFT becomes clear. It shows below the two methods compare as the size increase. The x-axis refers to the number of bits in case of the FFT or qubits. And this is the sort of like whole reason we're doing this. This is why we're here. So again, when problems are factored and a portion of the problem is implemented in quantum or with QPUs, problems that require factorization, like encryption problems, this is why people are interested. because of the speed increase that you get out of QFT. So that part made sense to me. And with that, I'm going to pause. Do you guys have anything to add here?
I like speed.
Yeah, and this is where it hit home too, because yeah, we whether you have 4 qubits, 5 qubits, 6 qubits, second qubit, you're still running that formula on a fixed number of bits, and you're getting back a result. You're not having to repeat or loop or anything like that. Whereas the classical computing, every time you add more bits, you're exponentially increasing that. And now one thing, and this is just the, I don't know, the data side of me, it's like, okay, so he says, oh, once we hit 30, 35 bits or qubits, we're still under a second for quantum. And so that makes me think, oh, are we really doing this somewhere? Is that a real value? Or is he just kind of arbitrarily is he just showing the relationship between a linear increase in computational power versus an exponential? I don't know. I don't know.
You have to look at like how many qubits are available. I think when we're looking at the IBM, there was like 128 you could get on basically the queue. And I know that Google Quantum was talking about, they're at like, I could be wrong, but like, it seems to me 64, and they really want to get like hundreds and hundreds and hundreds, obviously. That's like a big part of, the hardware race, if you will. But I do think, based on some of the hardware that's available now, that 35 qubits would be available. I think so. I think they could have tested that.
So it'd be interesting to see. Now, kind of going back, you hit on something in the very beginning that kind of opened my eyes, and I was like, okay, I sort of know what foyers are, some of the examples I saw on YouTube and stuff. But that key takeaway is that it finds patterns. Yes. And that's where it hit me, because you've been saying, your work in data intelligence and all that stuff, you're working with these larger and larger data sets. And so right here, they're talking about, okay, the larger our sample size, or the more bits we have to take a sample with, the better quality you have and the more you can look for. If you only have 4 bits, you're not going to have much information to identify the various frequencies or patterns. But if I've got 4,000 bits, wow, now you've got a lot more information. And so seeing a graph like this, it's like some of those hard, complex questions, Lynn, you brought up, they're near and dear to your heart with genomics or just something, the number of dimensions in things that they're looking at and data points are astronomical. And so, okay, if you got Jeremy's synthesizer, or if I've got some AV gear to rack and I'm trying to, cut out the noise and amplify the speaker, that's no big deal. That's little stuff. But when we start trying to find patterns in vast amounts of data, 1 year's worth of sales data or education data, that's doable. But when you start talking about genomics and DNA, I'm sorry, classical computers just can't handle it. This is where I see, oh, okay, so with qubits, we don't have that exponential problem. And this QFT is supposed to find patterns. Wow, if we have all this power in computing and we just learn something that finds patterns, that sounds a lot like what your goal is, taking this vast amount of information and teasing out, ideas and newfound knowledge that we haven't been able to even see before, just because our computers couldn't find the patterns. The data was just too complex. So that was kind of my overall takeaway from the chapter.
And in fact, I think the second to last chapter in the book is quantum machine learning. I mean, that really is a huge application. It's not the only one, but it's the one, as I've been saying, that I've really focused on. Well, as I predicted, this is a very chapter has a lot of information, but it was a fun journey with the two of you. So next week we'll continue along, because I want to make this, we're almost an hour. So would either of you like to pick up, or I can keep going? We're kind of doing this as a group, so it doesn't really matter to me. But if somebody is really interested in picking up from this point, you can go ahead, or I will continue. So you guys speak now, or you're stuck with me.
I think you're doing an excellent job, Lynn.
Okay, great. So next
I think
week-
you are. I also like the idea that whoever starts the chapter kind of finishes it. That way, they probably have the most invested as far as trying to be on top of it enough to present it. But it sounds like Jeremy will have a wealth of commentary on the
Okay,
inverse.
okay, great. Well, again,
yeah, the inverse, there was just some things about the diagrams that really annoy me
well, good.
as someone who's trying to learn something.
Next week we can talk about that. So, thanks for being with us live, and those of you that are watching online, again, you can jump in live anytime. That's going to wrap it up for this week. So I'm going to stop the recording.